Maths is numbers, and each of those numbers has a value. I might have a machine that I can put a number into, and it gives me a number back that is different, but is different by the same amount, or there's some rule that I can use to predict what comes out of that machine when I put a number in. We can use letters, A and B. We could use names, Harry or Joe. We could use anything really to represent my input and my output, as long as there's two of them. But we like to use X and Y, X being the input and Y being the output for some reason. I'm not entirely sure why. You have Google for that one. So basically, the letters don't mean anything on their own. They're basically just a placeholder that I would put a real number, like 1, 3, 57, 6 over 11, etc. The machine would do something to it, like multiply it by 3 and add 5, and then spit out a new value that was 3 times my original plus 5. The thing about this machine is that I can predict what each number will be. If I put 3 in, I know that it would multiply 3 by 3, which is 9, and then add 5, so 14. If my input was 5, I would multiply 3, so 15, and then I would add 5, so 20. If I did it for 2.156, I could get 3 times 2.156 plus 5. I can do this for any number on your number line, so I can visualize it. I can imagine a horizontal number line is my input, and whatever the output is for that input, I can put in it higher or lower vertically on this number line to indicate its actual output. This is the basic idea of a function and a 2D graph. I put something in, it responds, but the response is always in a way that I could have predicted every possible outcome. If I put in any number, 0, the square root of 2, a billion, 6 over 11 again. So pretend I do try and input all of the numbers one at a time from 0 and go up by a little bit each time. I want to know now how it changes over time. So when I go from 0 to 1, how much did my result change? 0's output is 5, so 1's output is 8, so it changed by 3. From 1 to 2, how much does it change? 2's output is 2 times 3, plus 5, which is 11. So it went up by 3 again. If I keep testing this, I would realize it rises by 3 for the output each time I go up by 1 for the input. This is the slope, or the rate of change, of this line. A crucial thing to note is that the slope, or the rate of change, requires 2 points to be measured to know how much it is changing by. It sounds pretty silly to try and find the slope at a single point, because I've got no idea what's going on around me at that point. It could jump to 1,000,000 in the next one across, or it could rise by a 0.5. It could even go down. So I need 2 points, one further along and higher or lower, and my initial point. I could then argue that the slope between these 2 points is the difference of the vertical over the difference of the horizontal, which makes intuitive sense. So the second output minus the first output over the second input minus the first input, or like y2 minus y1 over x2 minus x1, could be an equation that represents the slope between any 2 points, given I have 2 outputs, the y's, and 2 inputs, the x's. Because the slope wasn't changing as I went up or down the line, this is a linear equation. So whatever I input and whatever it outputs, it increases by the same amount. So if I add 1 to my input, I know the output will always be 3 extra. What about exponents though? Say my input, I square it to get the output. So 1 squared is 1. 2 squared is 4. 3 squared is 9. So we increased by 3 between the first interval. And then we increased by 5, and that's not the same amount that it increased by. Could I even work out how it increases by? Because, I mean, that line's curved. If we say that our function for some input x is x squared, so I square whatever I input and get that output, it's a curve, so I can't really find a slope or a line along that curve, can I? But I can get an average. So if at 0, the value is 0, 0 squared 0, and at 5 the value is 25, so 5 squared 25. I can say that it goes up by 25 every 5. My logic by proxy means it goes up by 5 for every 1. But the thing is, between 0 and 1 it only goes up by 1, because the answer at 1's 1, so it goes up by 1 over every 1, not 5. And this is an average increase. So essentially, the 5 view was correct when I looked at it from 0 to 5. If you look at the big picture, all is fine. But if you zoom in, you aren't actually that accurate. Again, it's just an average, a guess. So if we take that slope between 0 and 1, I realize for every 1 I go up by 1. Nice. What about 0.5 and 1? By the above logic, it should increase by 0.5 as well. But 0.5 squared is 0.25. so it must increase by 0.75 in between to reach that whole 1 by the time our x, or input, is equal to 1. The same logic applies all the way down. I could get the average slope between a millionth and 2 millionths, and still I would lose accuracy if I was looking at the slope between a billionth and 2 billionths instead. Can we ever get to a point where we were so infinitely small, so infinitely precise? Well, that would be an upward change of 0 over what a rightward change of 0, which makes no sense. 0 over 0 doesn't equal anything in our current scope of maths. So I'm going to do a mathematician's favourite thing, pretend. This is where we use a little bit of wizard magic, but it should still sound like things make mathematical sense. This should still make 100% logical sense. So I'm going to try and find the slope upward between my first input and the input right next to it. And I mean right next to it. Basically my first input plus 0, or an infinitieth. So small the gap basically doesn't exist between these 2 points. Since we can't call it x plus 0, we're going to call it x plus h. I know that h is basically 0, but if we call it 0, it'll be 0 divided by 0 again. So let's pretend it's a real number for now. So I know my 2 inputs. I want to see how the slope changes between them, x and x plus h. What are the outputs? Well, the output for x, we can call it anything really, y, a, b, but I'm going to call it x squared, since that's actually what the output is. Because our function's x squared, so for the input x, our output's going to be x squared, is literally the input and square it. What about the output for our second input, x plus h? We have to square the whole input, which again is basically x plus 0, or also x, but we're still pretending that h is a real number. So we do x plus h all squared. Now, if our slope is how much the line goes up or down across our 2 points measured, I could say the slope, once again, is equal to the output vertical of the higher second point minus the output vertical of our first number, or x plus h all squared minus x squared. I could then say this value is divided by the horizontal difference, so it goes up as it goes right, this much. The horizontal value is the second input, x plus h, minus the first input, which is just x. So the bottom can be simplified to h, since x minus x is 0. Normally h would be 0, so the fraction wouldn't work. But hold your horses, this is h we're talking about, totally not 0. Let's turn our attention to the top. To get rid of the little 2 on x plus h, we can expand those brackets using mathematical laws. If you haven't learnt those yet, I've got another video for that in the description. Basically, it expands to x squared plus 2 lots of x times h plus h squared. So the x squared and the minus x squared cancel out. We're now left with 2xh plus h squared all over h, which normally would be 0 over 0. But this is h we're talking about. It's a letter. If h is in both top terms, I can basically take it and put it on the outside of a pair of brackets, doing what is known as factorizing. If I'm multiplying everything by a common letter, I can pull one of them out of every term and put it on the outside. Now, doesn't that look like I'm multiplying everything by h, but then dividing everything by h? Why would I do that? It's just the same value. If I multiply and divide something by the same number, it's like doing nothing. So let's cross them out. They don't exist anymore. Get out of here. Gone. Now I'm left with 2x plus h. You know what I said before that h was a letter and not 0? You know I lied. It is 0. Get that thing out of here. 2x plus 0 is the same as 2x. So we did the slope equation, the change in up or down over the change in left or right, and that was supposed to be 0 over 0 because I basically used 2 points that were essentially the same point, so close together. But we're left with something that's a real value. 2x, that's not 0, it's not infinity, it's not undefined. See, we did a little bit of mathematical magic called differentiation. This means that wherever along our number line the input is x, I can predict that the numbers right above and right below are 2 lots of x more or less than our actual output at x. This makes sense, since now the rate of change, or how much the slope will go up or down by, will change itself. It'll change as we go along the line. So at 9, the rate of change is 18, since 2 lots of 9 is 18. But at 3, the rate of change is only 6, which makes sense. The curve seems to get steeper and steeper as we get higher and higher numbers. So differentiation is simply finding the slope, the rate of change. One of these input-output functions, but when it constantly changes, so it's a curve. So we cheat by finding the slope between essentially what is a point and itself, but it's not, but it is, but it isn't. if we pretend a distance of 0 between our 2 points of measurement isn't actually 0, right until the last second, we can actually find a value output by the end. And that's the goal of differentiation. Oh, and before I go, I hope you understand what I meant by a function having an input and it giving me an output that I can predict. And I can predict how much it changes by if I increase or decrease my output. You might have also heard of another type of calculus, integration. This and differentiation are the two major sub-concepts of calculus. Now there is more to it than this, but broadly, integration can be thought of differentiation's undoer. It's like multiplication is to division, as integration is to differentiation. Integration can get you to have the rate of change at which my function changes over time, and I can basically solve for what that original function was. I hope this made sense. Apologies if I'm speaking a bit slower than what you're used to, but I feel like it helps really articulate what the heck is going on here, because it is mathematical magic, but it is so useful in our world and has achieved so much. Thank you.